Hello, this Science of Sport video is for Unit 7 Biomechanics, where we're investigating linear motion. Specifically, this is relating to A2 on the spec, which is about speed and velocity and does include distance and displacement. So there's the specification. And it's worth just taking a look at that and looking at the language that they use in terms of their definitions, the units involved. It gives you some hints in the sort of examples you might use. Obviously, you need to make your own examples in your work. So let's start off by looking at distance and displacement. Here's an example, the London Marathon. So the question would be, what is the distance travelled by athletes in the London Marathon, and what is the displacement travelled by athletes in the London Marathon? Well, for those of you that may have experienced it or watched somebody or supported somebody, you will know that the distance is just over 26 miles. It's 26.2 miles. So the start would be over here by the base of the arrow. You follow the mile markers all the way in this wiggly woggly route, eventually getting to 26 miles over here by Green Park. However, the displacement that athletes have travelled is only 6 miles, and we measure displacement from the start directly to the finish. So it basically is represented by this red arrow. Similarly, here's a 200-metre event. So question would be, what is the distance the athletes travel? Well, they run round the track and they end up at the finish line and they cover 200 metres. However, if you ask what's the displacement the athletes have travelled, you would need to measure directly from the start along the dashed line to the finish, which, as you can see, is about 123.8 metres. The distance is all the way around, all the exact distance that they cover, 200 metres. And in actual fact, it's worth noting here, because this diagram nicely shows, distance doesn't really refer to direction, where you're going, whereas displacement measures should have some kind of reference to a direction. So in this case, they've said the displacement of the athletes is 123.8 metres at an angle of 36 degrees. That's the direction that they travelled that displacement in. Other examples, so let's get some key facts down about distance. Distance is the sum of all movements regardless of direction, so wherever the athlete goes. So on my diagram on the right here, it's all the wiggly line. This is the distance that the path that is taken by the cyclist, the runner, whoever it happens to be, the car. It is the length along the path that the object has travelled, the actual route that they take. In contrast then, displacement is final position minus initial position, and gives you the change in position. So from here to here, what's the difference in their position? So displacement is a change in position during a time interval. It's the difference between a person or object's final position and their initial position. And obviously it does account for direction in this context here. So this is almost like if you know the phrase, it's 3 miles as the crow flies. It's the most direct route from A to B, and it should have a directional value. It could be degrees, it could be north-south, it could be left-right, but it should have some reference to direction as well. So there's a little bit of a difference between distance and displacement. Genuinely in sport and in life, we tend to use them interchangeably. We don't tend to, I travelled 3 miles northwest, or at 28 degrees. We don't say that, but you need to know the technical differences between the two. Here's another little example of displacement. So this athlete kicks the ball, and the angle down here, so the ball starts at the foot, ends up at this point up here. This is the displacement, this S dark line. This would be the directional reference, the degrees, whatever that must be. It looks about 45 degrees at the moment. The distance would be this red line. The ball actually travelled up in the air a lot further, as you can see that the displacement is. Sorry, let me just pop back. So displacement should have a reference to the direction of travel as well as how far it went between the start and the final position. And that makes it a vector. And we'll look at vectors and scalars. You should actually know about those already. Examples then. Calculate the distance and displacement of 4 by 100 meter freestyle swim relay. So this tends to be in a 50-meter pool. The athlete will swim there and back and then tag the next person. So after the 4 swimmers have gone, the displacement would actually be 0. They always end up where they started. However, of course, in total, the swimmers have travelled 4 times 100, that's 400 meters. So the distance is 400, the displacement is 0. So now we're going to look at speed. Here's the spec information about it before we look at it specifically. You can always pause the video and look more closely at these. You may in biomechanics refer to instantaneous speed, but most likely you're looking at average speed over a certain distance and the time it took an athlete to travel that distance. What was their speed? That's average speed. Here's the definition. This Stafford, Brown, Ray and Aldridge is actually from the yellow sports science textbook. Please, I would always encourage you to use either the blue or the yellow textbook definitions rather than anything from the internet. It's slightly more credible. You can get the citation so we know who the authors are and the year is. It's a much better way of representing and putting in your this information in your bibliography than grabbing some random website from the internet, which may be less credible. So speed is, or average speed is, how quickly a body or object has moved from their start position to their finish position. It's the rate of change of distance or the rate of motion. And the unit is, or the symbol is S. So again, you may know that already. It's measured in meters per second. So there are a few different ways of writing meters per second. Ultimately, I would stick to one of them. So for example, you could use this method, this unit here. Whatever one you pick, stick to it and use it consistently throughout your work. But this is probably a good modern way of representing the speed units. So for example, if Johan Blake is travelling at 10 meters per second, every 10 meters, it takes him a second to travel that distance, on average, over the 100 meters. So speed is calculated because you will need to show some workings and give your own examples. Can I reiterate your own examples? Not any from my videos, not any from other sources. Use your own data. It's pretty easy to create some yourself, and you need to demonstrate that you know how to do the calculations of speed. So speed is distance over time. This sort of triangular formula is quite useful for some of the calculations you may need to do, but we want distance over time. This is distance travelled over time. So speed is distance over time. Nice and easy. So there we are. Usain Bolt, as an example, ran 100 meters in 9.58 seconds. What was his average speed? So we do distance over time, 100 over 9.58, and that gives us 10.43 meters per second as his average speed over that 100 meters. So velocity then. Well, how is velocity different? Now, speed just talked about the size of the magnitude of the speed, how fast. It's a scalar quantity, whereas a velocity is actually a vector, which means that not only do you need to represent how fast the athlete or the object is travelling, but you should give a directional reference to it as well. Again, we don't tend to do that in reality. We don't say he ran 100 meters south. We just tend to talk about speed or velocity interchangeably. So again, you can have average or instantaneous velocity. This average means over 100 meters, what was the average velocity that they were traveling at and in what direction? Instantaneous would be in any moment within that 100 meters, what was their velocity? But we tend to do this. The reality is, of course, when we look technically at how we calculate velocity, sometimes the outcome is meaningless. That's why we tend to use it in the same way as we do speed. So by definition, velocity is the rate of change of displacement. Notice that speed, let me just go back to speed. Speed uses distance over time, and velocity uses displacement over time. So velocity measures the rate at which a body or object has been displaced or experienced a change in position. You can see the language is the same as the velocity language. Again, this is the yellow textbook definition, a good source. Either of those books will have a good definition for you. Its unit is meters per second, same as speed, but you should add a directional reference there if we're being technically correct. And the symbol is V, so speed was S, velocity is V. Here's our example, the same example again then. If we were going to represent Johann Blake's velocity, we would say he was travelling, should say a velocity of 10 meters per second east, or 10 meters per second in a positive direction, or 10 meters per second at an angle of 27 degrees. There should be some directional value there. So there we are. How do we do calculations? Because again, you need to make up your own calculations and give your own examples and your own values. It can be from your sport, it can be from any. It's so easy to make up something. Velocity is calculated by total displacement over time, so that the displacement value over the time taken. These all kind of mean the same. So this one up here is the final position over the initial minus the initial position. This is the final time minus the start time. It just gives you the change in position over the change in time. This triangle, you'll see quite often actually means change in. So change in position over change in time. Here's an example then. Andy Murray serves a tennis ball to Nadal. It travels at 9.5 meters south in 2.1 seconds. So it travels that displacement and that's the time it took. What's the average velocity of the tennis ball? So we need to do displacement over time. So we do 9.5 meters over 2.1 seconds and it gives us a velocity of 4.5 meters per second with our directional reference south. Again, not realistic. So another thing you will need to be able to explain and translate with and I have no problem with using these sorts of generic graphs. That's not a problem at all in your work. You need to represent what these graphs show. These are distance time graphs, and they basically say over time, what is happening with the distance of the object? Is the distance changing or is it not changing? If it's changing, it's moving. If over time the athlete or object's distance is changing, then the athlete or object is moving. If over time the distance is not changing, then it is stationary. So let's look at the first couple. Here we've got time on the bottom axis. You can't quite see the time unit there, but this is time, and of course the d is distance. So over time, this distance, this object's distance, is not changing. And what that means is the athlete is not changing position over time. Therefore it is still, and the velocity would be 0. The second graph here, over time, whilst the current position is further away, this i.e. higher up this axis, the position of the object is still not changing. And this again would mean that the object is stationary at 0 velocity. It's probably just further away than this object. Third one then. Over time, the distance is consistently getting further away, changing, which means that it's likely the object is travelling at a constant velocity. Over time, it's getting further and further and further away proportionally. So this linear relationship between distance and time represents a constant velocity. This penultimate one then, over time, the distance gradually gets disproportionately greater, which suggests that this object, as time goes by, is speeding up, and increasing velocity. And when an object gradually increases velocity over time, that suggests that it is accelerating. And therefore you've probably figured out this one. Over time, the object starts at a greater rate of velocity change, which then flattens, which suggests that the object is slowing down and showing deceleration. So again, pause the video, have a look at the graphs, look at the text beneath just to help you translate the what the graphs show in terms of any object velocity. We might be talking about a ball, a car, a cyclist, or a person running. It's an object. Again, in your work, I've no problem with you using these as long as you translate them in your own words and using your own examples. So as well as distance time graphs, this is what we just looked at, you will need to be able to understand and translate velocity time graphs. So all we've done is we've got the time on the x-axis still, but instead of distance over here, we've got velocity. And it's very similar in the meaning and the translation. So for example, over time, this object's velocity does not change, which suggests that it is at a constant velocity. It is moving, but it is not accelerating or decelerating. The velocity of this object remains the same. This graph suggests that at the start of the time of this action, the velocity is high, but over time the velocity decreases, which again you might realize shows a deceleration of the object over time. And then conversely, this one shows an acceleration of the object over time. As time goes by, the velocity increases and increases and increases. So again, there's the written translation. No acceleration, but constant velocity. Deceleration and acceleration. Now, a lot of our sports, especially the games that we play, involve us changing direction, speeding up, slowing down. And this is just a very simple graph, which probably looks more complicated than it is. But if you go bit by bit, it kind of makes sense. So we've got an object stationary here, 0 velocity, which you can see increases velocity slowly. So the gradient there, the steepness of this line, indicates whether it's a gradual acceleration or a more rapid acceleration. So this object sped up or accelerated slowly, then accelerated more rapidly. The velocity in this phase is the same, it doesn't change, so there is motion, but it's constant velocity, constant speed, no acceleration or deceleration. But here, there's a deceleration to the point where the athlete or object is stationary here. There's 0 velocity. Over time, there is no change in velocity at 0, so they are stationary at this point. And then there's an acceleration in a different direction, and going below the line here indicates different direction. So this athlete or this ball has hit something and is, bouncing back in the original direction, the opposite direction, or the athlete has turned and is accelerating in the opposite direction. And here, the object is moving at constant velocity in the opposite direction. So above the line and below the line can show where velocity, shows velocity, but shows velocity in a different direction. Remember, velocity is a vector, and you need to account for how fast something's traveling, the rate of change of velocity, but also the direction of the velocity.